Hi goers, welcome to the remaining chapter 6 material. So today we're going to talk about the remaining alkene reactions that you have. I may do it all in one video, I may do it in two separate videos. We're just going to see how far we can get. Okay, so we've already learned a lot of different reactions for alkenes. More specifically, we've learned how to form alcohols from them, and we've also learned how to form ethers from them. But now we are going to learn how to form haloalkanes or alkyl halides from these alkene starting materials. So this first reaction is called halogenation of alkanes, and your main reagent that you're going to have is some sort of halogen. And we pretty much are only going to see chlorine and bromine in this class. But the other molecule that is present on these arrows is some sort of inert solvent. So we see in this kind of reaction description up here that we have chloroform and dichloromethane. They're not actually involved in the reaction, but they aid in helping to bring these reagents, the chlorine and the bromine, close enough proximity to that alkene, to actually facilitate that reaction. So their role is to really just, promote the reaction. It's not really going to have any different impacts on the products that you form. So for your purposes, you can actually kind of ignore them, but do be aware that they do exist and that they are present. Okay, so one common note I just want to say is that if you see the word or the letters DCM, that's what dichloromethane stands for, DCM. In my organic lab, we always use the abbreviation DCM to refer to dichloromethane, so I thought it'd be kind of cool to show you guys that that's the abbreviation that exists. Okay, so this is a specific type of mechanism that we have not seen before, and it's called a concerted mechanism, and it is also the first stereospecific mechanism that we have, okay? So let's kind of just talk about this. Let's talk about this in terms of the mechanism first, and then we'll get faster in terms of predicting the products. Okay, so essentially we have some sort of pi bond, and then we're gonna have some sort of a halogen. So I'm just gonna draw that depiction right now. Okay, so that's my starting material, and this is my halogen. So the mechanistic arrows would be that nucleophilic pi bond attacking the chlorine, and that also breaks this chlorine-chlorine bond to facilitate the formation of free chloride. But why it's called concerted is that the minute that pi bond attacks this chlorine, we're going to start to develop some partial positive character right there because, we're taking electrons away from that position. So then there's a lone pair on this chlorine that is going to equally as likely come back and attack to stabilize that deficiency. So what results is something called the Halogenation bridge. Okay, so a Halogenation bridge looks like this. Okay, so that's the result of the Halogenation bridge from step 1, and we also have free chloride. So where is that free chloride now going to react in this mechanism? Well, we have two positions. We could really react at that position, or we could react at that position. So which one is it? We don't know unless we draw resonance structures. So one of the resonance structures would show, okay, so that would be the result of doing this series of mechanistic arrows. Okay, so that would be the result of that. We would just take those electrons from this carbon to that chlorine and make it a lone pair. And then the next series of mechanistic arrows to get the next resonance structure would be something that looks like this. Okay, so resulting structure would be okay, so we see that we have two carbocations. Well, let's kind of rationalize why that chloride anion would attack one position and not the other. Well, the first thing we do when we see carbocations is classify, obviously. So in this left intermediate, or this left resonance structure, we see that we have a tertiary benzylic carbocation. Okay, on the right side, we see that we have a secondary carbocation. Oops. Okay, so now it should make sense why this chloride anion wants to attack the more substituted position of that Halogenation bridge, because that intermediate is more stable than this intermediate. So attack isn't going to happen there, but it's going to happen at this position. Okay, so the result of that mechanistic step would be two chlorines on each of the carbons where that pi bond used to be. Okay, but this is not the correct answer, because if I were to have this answer on my test, I would see that I have 2 chiral centers. So 2 chiral centers tells me 4 total stereoisomers, but I'll tell you right now that there's only 2 total stereoisomers that you should be drawing on your test. And that is where the stereospecificity argument is going to come into play, okay? So stereospecificity is different from regioselectivity in the sense that we're not having just a specific location being attacked, which was Markovnikov's rule, but we're also having a specific arrangement of wedge dash orientation occur for these molecules. So let's kind of go back to that first mechanistic step that we did over here. Okay. So when this halonium bridge was forming, remember that pi bonds are really just sp2 orbitals with each carbon having an unhybridized p orbital that overlaps, and we have this, massive, p lobe on the front face and then a massive p lobe on the back face. So I can kind of draw that as this is the sigma bond framework, and I will draw a circle and a circle, okay? So the circle positive represent the 2 p orbital front-facing lobes coming out of the page, which would morph together to really just form a big conglomerate of plus on the front face. But likewise, on the back face, you would have negative phases, so you have a huge conglomerate of the negative charge guy. Okay? So it's hard to see, in this page depiction, but if I were to rotate that, what that would look like essentially would be this. Okay? So positive, negative. The positive phases, you can attack one face, or the negative phases, you could attack the other face. Okay? So that's kind of what we're talking about here with pi bonds. So essentially, that bridge could have formed on the wedge configuration if it attacked the front face or the positive face of that orbital, or it could have attacked the back face. Something like that, okay? So that chloride anion that was generated is still regioselected, and that no matter what intermediate you have, it is going to attack the more substituted position. But the way that chloride anion is going to come onto the molecule is restricted to the specific stereochemistry that we have present from that halonium bridge. So in structure A, we have a wedge orientation for that halonium bridge, so that incoming chloride anion is going to be on a dash configuration for that halonium bridge. So essentially, the resulting stereoisomer from this is going to be a dash chlorine on that tertiary benzylic position and a wedge chlorine on that secondary position. And then over here for structure B, you are going to have a wedge configuration chlorine, a dash configuration isopropyl, and then a dash configuration chlorine. So these are your 2 major stereoisomers. This could be confusing. Those are your 2 major stereoisomers, not 4 total stereoisomers. Okay? So that's pretty much how this mechanism works and all the different arguments that we have to consider. So let's kind of just jump right into predictive product sections. Okay? Okay, so for letter Q, we see that we have, a pi bond, and we see that we have a tertiary position right here, and we see that we have a secondary position right here. Okay, so we know that where that bromide anion is going to attack, it's clearly going to be the tertiary position. Okay, so what you want to do is keep the sigma bond framework intact. So essentially, I want to draw this. Okay, and if I were to have that bromine come on a wedge in terms of that halonium bridge, I would have on this carbon right here a dash bromine, okay, and then the wedge bromine, right here, okay? So this is the one, so this bromine was the orientation of the halonium bridge to begin with, and then this bromide was the nucleophile that came in, okay? So if I also want to draw the other major stereoisomer of this, again, you keep the sigma bond framework intact. Think about if I were to keep it on if the halonium bridge came in on the dash configuration, that a bromide anion came in on a wedge configuration, which forces the other guy on the methyl. And then we said that the original bridge was a dash, so that should make sense. So these would be my two major stereoisomers. I hope we're getting better at that. Okay, so then another example, letter R. So if those bromines came on a wedge, okay, we would have, it doesn't matter which location you would attack with the bromide anion because they're both secondary carbons no matter what. So let's just say we formed that bromide bridge. Notice how it would be the same as saying I formed the dash configuration, okay? Because I can just pancake flip that. And then my bromide anion can attack either face, doesn't matter. And the resulting structure would be something that looks like, okay? Or it could have attacked the other position. So let me change color. So if I wanted to change here, or it could attack here. And then that resulting structure would have been no matter how you flip these, they are not going to be identical, okay? So these are your two major products from your reaction, okay? So let's keep moving on. So in letter S, let me make some more space over here. Okay, so in letter S, notice that we have a tertiary position right here, so that should scream something to you. And here we have a primary position, okay? So let's keep our same starting material. If you are not doing any chemistry with a chiral center, you leave it the way that it is, okay? So if let's say that my bridge came on a wedge, okay, something like that. So then that my bromide anion is going to attack the more substituted side, okay? So essentially, we should get two diastereomers. So we would get dash bromine, wedge methyl, that, and then wedge bromine. And then you also get the other diastereomer, okay. So I did something wrong on purpose. So notice the stereochemistry of those bromines. If the alkene is terminal, that terminal carbon is not going to have any stereochemistry, and you don't have to memorize that. We know that because there are two hydrogens. So we know that that's not a chiral center. So it'd actually be wrong to put these substituents on, wedges and dashes. So in theory, the real answer should be okay, so those two structures. All right, hope that helps. We have one more final example. So I'm basically just going to draw right on it. Essentially, we would have one with a chlorine here, a chlorine there. Because there's no difference in substitution, we don't have to, consider the specific Halogenation bridge that's forming. And then also, we would have that one and that one. Okay? So I hope that helps with this specific reaction, so we can move on to the next one. All right, so the next major reaction is called halohydrin synthesis. So notice from the last reaction, which was halogenation of alkanes, we just had a halogen and some sort of inert solvent react. With halohydrin synthesis, we changed that inert solvent to now water. There's a huge consequence in doing that because the reactivity of an inert solvent, hence the name inert, is very different from the reactivity of water, and it's going to come into play here. Okay? So essentially, what we have going on is that we have that same alkene starting material and we have some sort of halogen. And that is going to be the same sort of reaction that we saw before in terms of concertedness. So we are going to see, directly to this step, either this guy or okay, so now your next reagent is going to be water, okay? And then that water molecule is going to do the same exact thing that we saw. It's going to attack the more sterically accessible side of this halonium bridge, and also the more substituted position of that halonium bridge, because it has more partial positive character. So essentially it should be something like that, and it should also be something, let me change color, it should also be something like that. Okay, so the resulting structures from that would be oops, I'm sorry, I did this wrong. Okay, so that would be the resulting structure from this guy, and then there would also be this structure. Okay, so those are the two major stereoisomers for this reaction. There is a deprotonation step in the mechanism where free bromide, so like, in theory, this really was water coming in, so that free bromide just really deprotonated. I skipped that in the mechanism. Okay, so that's typically, how we form these halohydrants. Halo meaning halogen, hydron meaning water or alcohol. Okay, so that's a halohydron. Okay, so we can kind of now predict the products a lot quicker. So we see that we have a secondary carbocation destabilized via induction, and then we have a tertiary carbocation that's also destabilized but farther away. Okay, so we know that water is going to attack that position. So essentially, we are going to get this series of products. We know the alcohol is going to attack on that side, on the tertiary side, but that chlorine can either be on a wedge or it could be that configuration. Okay, and that's it for that guy. All right, so let's keep moving. Okay, so I think we're getting quicker now. So we can tell that we are going to get an alcohol coming in on that tertiary carbon right here. This is our secondary carbon, so that's where my halogen is going to be. Okay, so now let's think about the stereochemistry. If that chlorine bridge was on a wedge configuration, then that alcohol was a dash configuration. Okay, so let's kind of just draw a structure that looks like that. So if that bridge was on a chlorine orientation, that alcohol must have been on a dash orientation. There's also that there. Okay. And then if the chlorine bridge was on a dash configuration, that alcohol came on a wedge configuration, making that methyl a dash. Okay, those are my two products for this. Okay, keep going. We have a tertiary position here. We have a secondary position here. So essentially what I'm going to do is keep this all in plane. We are not playing with the stereochemistry of that isopropyl group, so leave it the way that it is. If the bridge was on a wedge configuration, we are going to attack on the dash configuration over here. So the wedge bromine. Okay. And I'm sorry, there was also a methyl here. And also, if that bridge was on a dash configuration, that would give us a dash bromine there, a wedged hydroxyl, and a dash methyl. Okay, so those would be the two structures there. Okay, and lastly, an intramolecular ring closing. So, we started introducing this topic back to, exam 2 material, where we saw, if we had an alcohol starting material in the pi bond, as well as instead of the halogen, we saw H plus as a catalyst. That H plus would have formed a secondary carbocation. We would have had a 6-membered ring. You would have had something that looked like that. And then on carbon 6, you had a methyl. Remember, that was how we formed cyclic ethers, okay? So the same thing can happen under halohydrin synthesis conditions. So essentially what happens is that we form this halonium bridge. And then since this water or alcohol functional group is already in the molecule, it's just going to come in and attack itself. Okay, so that's a 1, 2, 3, 4, 1, 2, 3, 4, 5, 6, carbon ring. So let's draw the 6 carbon ring and label it as such. Okay, so on 6 is where we attacked, so we should have a carbon 7, which is carbon 7, and a chlorine sticking out like that, okay? But remember that we just formed a new chiral center from doing that. It wasn't stereospecific in the sense of how my reagent was added in, but it was stereospecific in the end where we saw that we had a wedge here or a dash there. Okay, so those are my 2 molecules. All right, and that's going to conclude all I have for this